Welcome to Chapter 18, Aldehydes and Ketones. Okay, so naming of aldehydes and ketones. So we have 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7. And as you can see, you have a ketone on carbon number 2. And so this would be 1, 2, 3, 4, 5, 6, 7. So it would be 2-heptanone, or you could write heptan-2-one. Okay, so the next one is 7 carbons. 1, 2, 3, 4, 5, 6, 7. And we have a ketone on 1, 2, 3, 4. 1, 2, 3, 4. Here's our ketone. And then 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7. So now this is 4-heptanone, or heptan-4-one. Okay, the next one we have 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And this is an aldehyde. Your aldehyde here, CHO, will always be on a terminal carbon. And that actually would be 1, 2, 3, 4, 5, 6, 7. You don't have to number it because it always has to be on that terminal carbon. So that's heptan-al. You could number it, but you don't have to. Okay, here we have phenyl, a carbonyl, and another phenyl. So this is, I guess you could call it diphenylmethanone. That would work. I think it's also called benzophenone is the common name. Okay, so the next one we have 1, 2, 3, 4. And it's an aldehyde. You can see the CHO. So CH2, 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 CH3. That is butanol. Okay, the next one is acetone. So that's the common name, is acetone, or 2-propanone. Okay, the next one we see we have an aldehyde here, and we have one. Now when you have in parentheses here is a substituent onto that. So let's just keep 1, 2, 3, 4, 5, 6. So we have 6 carbons, 1, 2, 3, 4, 5, 6. We have an aldehyde on carbon number 1. On carbon number 2, we have a CH3. So you can see the CH3 here. And then, so that's 1, 2, 3. And then on carbon number 4, you have a bromine, because you can see this as CH. And so what is this called? 1, 2, 4, 5, 6. So it's 4-bromo. These substituents are usually put in alphabetical order. B comes before the M for methyl. 2-methyl hexanol, Al, for the aldehyde. Okay, this next one here, we have a phenyl, and we have a carbon-carbon double bond, and then we have an aldehyde. So you could do 1, 2, 3, and you have an alkene there. So pro pro, and then dash 2-ene 1-al, and then you have 3-phenyl. Propene 2 or 1-al. Okay, and the next one we have 1, 2, 3, 4, 5, 6. Let's draw 6 carbons. 1, 2, 3, 4, 5, 6. First carbon has an aldehyde on it. Second carbon has a carbon-carbon double bond on carbon number 2 to 3. And then we have 4 to 5, we have another one. And so that's 4 to 5. So we would call this 2, 4 dash hex hexadiene 1-al. Hexadiene 1-al. Okay, so problem number 2. Let's start with H. H would be this compound here, this diol. Where is G? The G? Wait a minute. Maybe I had G. Okay, let's start with A. A is cyclohexanone acetal. Okay, so that is A. And then Tollin's reagent, you're going to get no reaction there. Okay, so that's no reaction. Dilute chromic acid to E. The acid's going to cleave your acetal to give you an aldehyde, and then the aldehyde will oxidize to a carboxylic acid. So that's structure E. And then the mercury with zinc, HCl, that's your Clemmensen reduction. And that will give you F, which will deoxygenate the ketone to a methylene and leave your carboxylic acid. So that would be structure F. Structure G is, okay, so we have, from A, you have a Grignard. Grignard's going to add to the ketone to make a tertiary alcohol, and your acetal is protected, so it will stay the same. So this will be G, but you add your acid, so actually it's going to then give you your aldehyde because it will cleave your acetal. So that's G. And then if you reduce those, that's where you would get H, which would be a CH3. So you get a tertiary alcohol. Okay, if you add acid and warm it gently, you're going to do an elimination at E1. So this tertiary alcohol get protonated and leave. And then you're going to get your most stable alkene, which follows Yatz's rule. So that would be I. And then J is this cyclopentyl magnesium bromide, and that will add to your aldehyde to give you a secondary alcohol that we see here. We've done G. Okay, so let's do B. PCC. So B is going to oxidize the secondary alcohol to a ketone and the primary alcohol to the aldehyde. And then we got A where the ethylene glycol is going, tosic acid will make the acetal. And then the last one we have here is A to C, and we're going to make the hydrazone. We have the acetal protected, so it's not going to react. And then the hydrazone basically right here is going to make N, another NH phenyl. Make that prettier. Okay. And that's called a hydrazone. Hydrazone. And that should be compound C. Okay, for each compound, name the functional group and show the compound that results from the complete hydrolysis. Okay, this is a ketal. And that would be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So there's your ketone on 2. And you're going to have 2 alcohols, 2 methanol. Okay, this one is a hemiketal. And you hydrolyze that, you would have your ketone, because that's the ketal. And you would get 1 molecule of alcohol, and it would be ethanol. Okay, this compound here, your alcohol portion is this, and this is an internal, and what you see here, this has 1, 2, 3 bonds, so there's a hydrogen there, which makes it an acetal. So if you were to cleave this came from an intramolecular alcohol, you would see that this is an aldehyde, and then this is the other alcohol, because remember you have to have 2 alcohols that add to the carbonyl to make an acetal or a ketal. Okay, this one is a ketal. So here's your ketone, and then this is your ethylene glycol that was your alcohol that reacted with that ketone. This one here comes from it's called a hydrazone. So let me write this, ketal. This is a hydrazone, and it comes from a ketone, and then that nitrogen you give it H2, NH2, and that's hydrazine, which is rocket fuel. This compound came from this dialdehyde, and NH2, NH2. This is called an amine, I-M-I-N-E. So it's actually a diamine, and this is, each one of these leaves a molecule of water to form the amine. So you can see there's your 2 hydrogens and oxygen that go to form your product. This one here, kind of tricky here. This one is just a bis ether. Bis means diether. So that's not going to hydrolyze. And you see that that is not This is the diether. This one here, this one is a formaldehyde here, and then this would be your alcohol. OH, OH. So let's see and double check that. Yeah, okay. Okay, proposed mechanisms for the following reactions. Okay, these mechanisms are quite long, so let's just be prepared. First thing that happens, okay, is protonation. So whenever you have acid and a carbonyl, the first thing you do is get protonation. Protonation, step 1. And then the second step, step 2, you're going to get nucleophilic addition. So nucleophile adds. So in this case, you have phenyl NH, NH2, and the primary amine will be the one that actually does the nucleophilic addition to the carbonyl, and then you get what we call a tetrahedral intermediate, and you just make sure you have everything here, and that's your tetrahedral intermediate. And this would be a positive charge. So we have positive charge here. We maintain the positive charge. Now step 3, you have to get a deprotonation. And so in this case, you could just use water is our the deprotonates because you had acid. It probably came from H3O+. So now water will go and deprotonate. So you'll have a neutral intermediate. Now, what is going to happen here, okay, let's go ahead and write CH3, NH, NH phenyl. What's going to happen is the next thing you're going to get protonation. This is step 4 of the alcohol. So you got H3O+, and this alcohol is going to get protonated. So now we have OH positive, NH, NH, phenyl. And now we're going to lose water. So step 5, lose water. And water is a leading group that gets it's an SN1, and you get a carbocation. So we'll come over here and write CH3, C plus, HNH, NH, phenyl. Now these electrons here, the lone pair on the nitrogen, will add, and sometimes you can even do this simultaneously, and make a, and call it a shift base. And now nitrogen has the positive charge. So the last step, and always the last step in these, so this would be step 5, step 6, deprotonation. And once again, you can have water come in, deprotonate, to give you a neutral product that's right up here. Okay, so to do the next one, we're going to do very similar. So the first thing we're going to get is protonation. Okay, so that's step 1. In step 2, you're going to get the nucleophile adds. So protonation, the nucleophile adds, which is your alcohol. I'm just going to write the products here. So OCH3H. Now you have a positive charge. So the step 3, you're going to get deprotonation. So we'll have water. Water can come in and deprotonate that to give us a neutral molecule here, OCH3, and that is called the hemiacetal. So the next thing that's going to happen is you're going to get protonation. So step 4 is protonation. So you've got acid, and the alcohol here is going to get protonated. And so you get something like this, protonation of that alcohol, and it will leave. So step 5 is the loss of water to generate the carbocation, it's SN1. So you get phenyl, carbon plus, hydrogen OCH3, and then you end up having, if you see here, you have another addition. So that's step 5. Step 6, you have the addition of another methanol, the nucleophile adds, and so you get phenyl OCH3, CHO, CH3. This one has a hydrogen on it with a plus, formal charge, so water is going to have to do the last step, which is deprotonation. Okay. Oh, this one's the Wittig, VITTG. So the Wittig, basically, you have triphenylphosphine. This is an ylide. So phosphorus has a plus charge. Your carbon is a negative anion, and it's going to attack the carbonyl carbon. You get nucleophilic addition. And the phosphine now will get attacked by the oxygen to make a oxaphosphatine, oxaphosphatine. So it's basically this 4-membered ring here. And then you have 3. And then what happens is oxygen is not going to let go of that. Phosphorus is not going to let go of the oxygen. So those electrons go there, and then the oxygen electrons will go towards that new CH2, and then you get your product here. Okay, so we have 3 more. Let's do this one over here. So this is the hydrolysis of a ketal. So first thing you're going to do is protonation, because you have acid and water. So these oxygens get protonated. Give you a positive charge, and then this will leave. So the second thing you do is the loss of water. It's not really the loss of water, it's the loss of a leaving group, and it gives you a carbocation. So that looks like that, and this is your carbocation. You get a resonance stabilized structure. It looks like this, with a positive charge on the electronegative atom. And then using this one for step 3, you have nucleophile adds. So water is going to add, and you have water adding. And now you have step 4, deprotonation. So water then will take away a hydrogen to make this neutral species. This is a hemiketal right here. So this is a hemiketal halfway. And then you're going to get step 5, which is protonation. So you're going to get a protonation. And then basically, these electrons are going to come down and kick that. So you're going to have a leaving group for step 6. And you're going to lose now the alcohol that made your ketal. And you're going to generate something that looks like this, the ketone. And the last step, step 7, is deprotonation. So water will then come in, deprotonate, and you will get your ketone. Okay, so we have 2 more to do. Okay, so the next one, this is an amine, and you have acid and water. And so this comes from an aldehyde here. So this is an aldehyde, as you can see here, and then this is an NH3 plus because it's an acid. So these hydrolyze, they go back and forth. This carbon double bond nitrogen, you can think of it as a kind of like a carbonyl. So the first thing it's going to do, step 1, is protonation of the amine of the nitrogen, the amine. So you get protonation, makes that a plus charge, just like you did with the carbonyl. And then that activates it for nucleophilic addition. So the nucleophile adds to the carbon double bond to the nitrogen. So this is step 2. So this will go right here. These are actually more electrophilic than the carbonyl. So now you have the addition of water. And so you want to get step 3, deprotonation, to get you a neutral species here. Now, think about where you're going. This is going to get, this has to leave. So it's going to get protonated. So H3O plus is going to get protonated. So this is step 4, protonation of the nitrogen. Which makes it a positive charge. Positive charged nitrogens are good leaving groups. And so now this is going to leave. The electrons here actually just push that to leave. And 1, 2, 3, 4. 1, 2, 3, 4. This becomes oxygen plus. There's your hydrogen. And then their last step, which is step 5, is deprotonation. So water, deprotonate that to give you your compound here. 1, 2, 3, 4. And it would get protonated at the nitrogen just because you're under acidic conditions. Okay, the last one is hydrolysis of this right here. So that is your ketone, and this is your alcohol. Let's see what that looks like. I'll rewrite it here. Alright, so how does that work? Step 1, you're going to get protonation of the oxygen, because you want that to be a leaving group. And then you get step 2, it leaves and generates a carbocation. These are kind of like an SN1 type reaction. They're acid and water. So this leaves, you get an OH, and it's still attached. And you got a carbocation. This is resonance structure here, you could see. OH there. So that is your resonance structure. So now step 3, you get the nucleophile, which is water, adds to the carbocation. And when that happens, you get a molecule that looks like this, OH2. And then step 4, you got to get deprotonation. So you deprotonate, use water to get a neutral substance, because it should be a positive charge. So then we redraw, OH there, and you get an OH here. And at this point, this is a hemiketal, so we got to do it again. You get protonation of the alcohol portion, so H3O plus has to get protonated in order to leave. Then you just redraw this. Oxygen has now a positive charge, so it can leave. And then you can imagine that this comes down here and leaves. So then you have leaving group, and that looks like this, OH. There's your diol. And then you have your ketone. It still has a hydrogen on there, so then your step, this was 5, this was 6. Step 7, you're going to get deprotonation. So water will deprotonate to generate your ketone. Okay, so for problem number 5, show how you accomplish the following synthesis efficiently and good yield. So here we just have to put in our reagents. And so let's see what our reagents are here. The first one, acetaldehyde, going to lactic acid. Basically you just need, so acetaldehyde looks like this. Potassium nitrile will come in here and do a cyanohydrin. And then H3O plus will give you lactic acid, because it will hydrolyze the nitrile to the carboxylic acid. Okay, this here is the Wittig reaction. So all you need is a phenyl triphenylphosphine with a CHPH. That should work. Okay, this next one, well, you could actually use okay, so the next problem would be to this problem here. Okay, so what you need is a reagent called sodium triacetoxyborohydride. Okay, so the reagent you want here is the sodium triacetoxyborohydride. So sodium borohydride normally has 4 hydrogen hydrides bound to the boron. This only has 1, and so triacetoxy sodium borohydride will reduce the aldehyde, or CHO, to a primary alcohol. And what's special about this reagent, it will not reduce a ketone. So you can see here that this would be the perfect reagent to reduce the aldehyde but leave the ketone intact. Okay, but what if you want to reduce the ketone and not the aldehyde? So in this sequence, you're going to have to actually do some protecting group chemistry. So you want to add a little bit of acid and ethane diol. And what that will do, that will react first with the aldehyde. And okay, so that will first react with, let's just draw this over, with the aldehyde and make the acetal. And then the second thing you want to do is, you'll just want one equivalent for that. And the second thing you want to do then is use sodium borohydride, and that would reduce the ketone to the secondary alcohol, but it would not affect the acetal. The acetal would be stable. And then the third thing you would do is add acid and water, and you could hydrolyze the acetal back to the aldehyde. And that would take care of that. This reaction here, let's do this one in red. First thing you want to do, once again, is protect the aldehyde in the presence of the ketone. So you want to do 1 equivalence of the ethane diol and some acid, and that is going to make your acetal. And then you can use the Wittig reaction. So the second thing you want is triphenylphosphine, and then a C. You look at that, you want CH, CH2, CH3, and there's your Wittig reaction, and that would give you your product. Well, then the third thing you would have to do is hydrolyze your acetal with H3O plus and water. Okay, so the next one is this one here. And as you can see that this double bond is reduced and the ketone's still intact. So basically just that's just a hydrogenation using a metal catalyst like palladium. This one here, you reduce the ketone and the alkene. So you're going to use rainy nickel. Remember, that's just nickel saturated with hydrogen. So there's your rainy nickel and hydrogen. This one right here, you leave the double bond intact, but you're reducing the ketone to a secondary alcohol. So sodium borohydride will take care of that. Okay, this problem is show how you would synthesize the following derivatives from the appropriate carbonyl compounds. So this here is a oxime. That's a functional group called an oxime. It comes from a ketone and a primary amine, which is called hydroxyl amine. And so when these come together, you lose a molecule of water, which is the two hydrogens here and the oxygen there. Okay, the next one here, you can see here is the amine, which is just a carbon double bond nitrogen. And so the way amines are formed are from a carbonyl compound. So there's your carbonyl right there. And then the primary amine here, so NH2. And to make that amine, you lose water, which is the two hydrogens and the oxygen there. Okay, this is another amine. And so the aldehyde comes from this portion. So we'll go ahead and draw the benzaldehyde portion. And then this, actually, scratch that. Not exactly correct. Okay, so let's try this again. This would be your amine, and this would be your ketone. So you can see where that's your ketone, and then your amine would be CH2NH2. And so to make that amine, you lose that oxygen and those two hydrogens. Okay, so this compound, you can see that that is a ketal. So this is your ketal here. And this is your carbonyl. Okay, it's on that second carbon. And then this would be your dialcohol. And it's a cyclic. So, and to make that you would need acid. Okay. Actually, you need acid with all these. A little bit of catalytic acid. So they all need acid. Okay, so on this one we have an amine. So it's the carbon double bond nitrogen functional group. And the carbonyl. Okay, so the amine portion, the carbonyl, and then this comes from the primary amine, which would be, okay, the amine portion, then is this part right here. Okay, for the next one, this is an acetal, and basically that's the ketone there, and two molecules of methanol. So once again, you need acid for this, and you need acid catalyst for that one, and that takes care of that problem. Okay, problem number 7. Um, Thioacetals, dicyane, carbonyl group, hydrolyze and dilute acid. So this is your thioacetal, and it's pretty stable, and then it can be cleaved using mercury salts. See that? Mercury 2+ salts are added at low levels to promote the hydrolysis. Okay, so the first one, show how you would make 2-methyl-1,3-dithiane from 1,3-dithiane. So 1,3-dithiane is this structure here. Okay, so that's 1,3-dithiane. Now, if you react this with N-butyl lithium, so what does that look like? 1, 2, 3, 4 lithium. That is a strong base. Okay, very strong base. And your acidic proton here would be between these disulfurs. So this strong base, I was trying to look up the pKa value of the dithiane, so I need to look that up. But anyway, this N-butyl lithium will deprotonate that hydrogen, and this will generate a carbon anion. And so that negative carbon now can react with an alkyl halide, such as methyl bromide, and do an SN2 reaction where the bromine leaves, and this adds the CH3 to that carbon between the two sulfurs. And so that's how you would make that compound 2-methyl-1,3-dithiane. Propose a mechanism for the acid catalyzed hydrolysis of this compound. So the mechanism then would be you add acid and mercury chloride. And so this acetal, mercury 2+, this is, whenever I see mercury, I think of it as a really big, fat proton. Okay, so it's going to coordinate with the sulfur. They're both big orbitals. They're big, okay? And they're going to coordinate. So that's like protonating. Sulfur behaves a lot like oxygen. So instead of the sulfur being protonated with a hydrogen proton, which is similar in size of oxygen, it gets protonated, so to speak, with the mercury. And then the water can actually add nucleophilically to this carbon, and that cleaves the carbon-sulfur bond. So what would that look like? You have your mercury, and you have your water that comes in, CH3H, and then you'd have deprotonation, so you can imagine water will then deprotonate. So the first thing is you have protonation, so to speak, with the mercury. The nucleophile water comes in and attacks that carbon, sulfur leaves, then you get deprotonation. So then we have this neutral species here, and then you can get more mercury. It's going to coordinate with the sulfur. And then it's a matter of this leaving. So these lone pairs then can push the sulfur to leave, and you get something that looks like this. And then you're going to have to get deprotonation with water to give you a neutral acetaldehyde. Propose a mechanism for how mercury might assist the hydrolysis, and that's pretty much it. So, okay, number 8. There are 3 dioxane isomers, one 2-dioxane, one 3-dioxane, and one 4-dioxane. One of these acts like an ether. It is an excellent solvent for Grignard reagents. Okay, that would be the 1,4-dioxane. You see that this is an ether. Another one is potentially explosive when heated. Well, that would be the 1,2-dioxane, because when you have this oxygen-oxygen bond, it is a weak bond. It's like a peroxide, so that would be explosive. And then the third one quickly hydrolyzes in dilute acid. Well, there you go. That would be, that carbon is bonded to 2 oxygens, so that would be an acetal. It says propose a mechanism for the acid hydrolysis of the third isomer. So, if we were to do that, you would do acid and water. The first thing you're going to do is get protonation of one of these oxygens. And then water is going to nucleophilically attack this carbon. The carbon is very positive. It's bonded to 2 oxygens. And then you're going to get the alcohol that's protonated to leave. So you got 1, 2, 3, 1, 2, 3. And now you have this carbon here, and it has 1 hydrogen, 2 hydrogens. So let's go ahead and put hydrogens in. And now it has OH2. Make sure you get your formal charge plus. And then water is going to deprotonate to make it a neutral species. So O, that carbon, 2 hydrogens, and OH. Then you're going to get another protonation again, H3O plus. And so because it's going to be a good leaving group at that point. And you still have this here. So this leaves, and go ahead and do this here. So you get basically OH, and then you got this formaldehyde that's protonated, and then you get H2O. It's going to deprotonate to give you your neutral formaldehyde. And that is the mechanism. Okay, so this one says predict the product's form when cyclohexanone reacts with the following reagents. So this is cyclohexanone, and that's an amine, NH2CH3. So basically the acid is going to protonate the carbonyl, because that's what always happens when carbonyls are in acid, and that activates them. And then you have a nucleophile that can come in and attack that carbonyl. It undergoes nucleophilic addition. So now you have this tetrahedral intermediate. 1, 2, 3. Now, basically what's going to happen now is you're going to lose the OH here and a hydrogen. And just for time's sake, instead of going through the mechanism, I'm just going to write the answer. Okay, so I'll do that for each one of these. Okay, the next one, cyclohexanone. This is an amine, by the way. You got cyclohexanone with excess methanol. So an acid, you're going to make the acetal. Okay, the next one, hydroxyl amine. What is that? That's NH2OH. And you got weak acid, because you only want it to be about a pH of 5, with cyclohexanone. So you're going to lose this oxygen, and you're going to lose those two hydrogens to make an amine. And it's actually a hydroxylamine. Actually, it's called an oxime. So what does that look like? NOH. So when the carbon double bond with the OH, that would be an oxime. Okay, the next one, ethylene glycol. That's ethylene glycol and para-toluene sulfonic acid. So it's just acid. You're going to get the cyclic acetal. So there's your cyclic acetal. This one, the next one here, phenylhydrazine. So this is phenyl. Hydrazine has two nitrogens, NH2. So this gives an NH. So it's this NH2 that's going to react. Weak acid. Like I said, you want it to be about a pH of 5. And you're reacting this with cyclohexanone. You're going to lose oxygen. You're going to lose these two H2s to make an amine. So put in your phenyl. Now, this is called a hydrazone. So when you have two nitrogens like that, that's called a hydrazone. It's still making the amine, basically. Okay, the next one, you have phenyl magnesium bromide and mild acid. So phenyl magnesium bromide. So of course, this is going to do a nucleophilic addition. And you're going to get a tertiary alcohol. Okay, the next one, sodium acetylide. If you remember that sodium plus acetylide is the carbon double bond. And you're reacting this with a ketone. So it's going to undergo nucleophilic addition. And you're going to get protonation because it's followed by a weak acid. So you're going to add the nitrile. We learned that a previous chapter. Okay, the next one you have a Wittig reagent. So in this Wittig reagent, we go from cyclohexanone and we react it with triphenylphosphine, CH2, and the Wittig reagent will add the CH2 here that was the ylide bonded to the phosphorus, and it will replace the oxygen and make the alkene. So this is an alkene. And the next one is a sodium cyanide. Sodium cyanide. And you're going to make the cyanohydrin. So that's going to do nucleophilic addition at the carbonyl. And you're going to get protonation. And that's called a cyanohydrin.